Hello and welcome back to Numerical Analysis. So my DSLR just decided not to work out today, so I'm recording on my iPhone. We'll see how the audio quality comes out. The video is usually pretty good. Anyway, so today I wanted to talk about Newton's interpolation method. So we already introduced it back when we talked about interpolation in general. We introduced the Lagrange interpolating polynomials, and also we did introduce the Newton's interpolating polynomials. Now, ultimately, these are all the same polynomials if they're interpolating, say, if it's a polynomial of degree n or less, and they're interpolating a n plus 1 points, the polynomial is uniquely determined. We can see that through the Van der Waals matrix because that's invertible, and if it's invertible, that means there's actually one solution for the coefficients. But there's different ways of arranging it, and so different bases to look at. And so one basis that we could use is just 1x squared all the way up to x to the n, and so that's what we do with the Van der Waals matrix. We can also use the basis that we get from the Lagrange interpolating polynomials, which are the polynomials of degree n that are 1 at the interpolation point and 0 at a specific interpolation point, and at all other interpolation points it's 0, right? So then it would give it, out of n plus 1 interpolation points, it gives it n zeros for each of those polynomials. So those would be uniquely determined by that setup. But the other one we really should talk about is the Newton's interpolating polynomials, and specifically we really need to go over this divided difference thing. So the divided differences are really handy, and in doing Newton's interpolation, there are a few advantages that you get. So first of all, if we change the ith interpolation point, then the first I minus 1, or the first I minus 1 or I polynomials that you use as a basis, they actually don't change. And so you only have to worry about changing everything after that. So there's less to do if you change your interpolation points to correct it than with the Lagrange interpolating polynomials, where every single one of your basis functions has to change. So that has that going for it. And the working out the coefficients through Newton's divided differences is actually going to be rather important for us. In particular, we're going to see it come up again when we start talking about numerical differentiation and numerical integration. It turns out that doing all of those calculus type things are really well assisted by doing interpolating polynomials, and having a nice convenient way of getting at the coefficients is rather beneficial. And so that's what we're going to do with Newton's interpolating polynomials. But yeah, so that's the idea. I think at this point you know what interpolating polynomials are, and so I'll leave you with that, and we'll jump into the lecture. Let's see if I can. Okay, so let's go ahead and take a look. So we're talking about Newton's divided differences approach. To interpolation. All right, so what we're left with is, so what we're looking for is we have this collection of points, xi and yi, say I running from, say, 1 up to some n plus 1. And we want to be able to get to a polynomial of degree n or less. And so generally that is that set. Okay, so that's what we're looking for. Is we're looking for a polynomial that interpolates these points. So such that pxi is equal to yi, right? Now, presumably we're thinking that yi is coming from some sort of function f of xi. Okay, so we saw that if we use these polynomials, say where we take n naught to be equal to 1 and n1 to equal to x minus x1, I think. Yeah, x minus x1, and 2 to be the polynomial x minus x1 times x minus x2, and etc. Then we can make up a polynomial, p of x, call it Pn of x if you want to just be specific about the polynomial degree, or the highest degree you can have, should be equal to this, where we have, say, a naught times n naught of x plus a1 times n1 of x, and so forth. So an times n of x. That is an unfortunate notation for these Newton polynomials. Okay. All right. So what do we do? Well, how do we get these ai's? Basically, for instance, if I want to get a naught, well, if I just go ahead and plug in take a look at p of x1, then, well, this is just the constant function, right? So this is going to be a naught times 1 plus this guy is going to be 0, and everything up is going to be 0. So plus 0 plus 0, because they all have this x minus 1 in there. So, ta-da! A naught is Pn of x1, but what is Pn of x1? Pn of x1 is supposed to be y1, right? So a naught is equal to y1. All right, so how do I find a1? Well, if I want to find a1, I take a look at Pn of x2. So that's going to leave us with a naught times 1 plus a1 times x2 minus x1 plus 0 all the way up. And this should be equal to y2. All right, so I kind of anticipated that a naught was going to be equal to this. I really should have started writing that first. But, you know, it's technically true. Just to avoid confusion, we'll just write that. Okay, so let's go ahead and solve for a1. So a1 is going to be equal to y2 minus a naught divided by x2 minus x1, right? And we know that a naught is just y1, so it's y2 minus y1 over x2 minus x1. And that's what we got. Okay. So now let's see if we can come up with a much more general way of doing it. We saw that if we had a naught, we can come up with a formula for a1. And in general, what we said was that we're going to take a look at these coefficients, which we can now write ak is equal to, say, y1 up to yn plus 1. And this is the forward difference notation. You know, I honestly can't find any nice place where it has a standard notation. Like every book I look at has a completely different way of writing it. So I started with this, and so I'm just going to stick with it. Okay, so we define this recursively. All right, so the way we define it is we take this, that shouldn't have n plus 1 there, it should just have up to k. So we define this this way. So y1 up to yk is going to be equal to, say, y2 up to yk minus y1 up to yk minus 1. And we're going to divide this by xk minus x1. Okay. So we see that each of these are of length k minus 1. And so you would basically take the same formula for k minus 1 and apply it again. And we know that eventually it'll terminate just because we only have a finite number of terms. So So how do we come up with a nice efficient way of doing this? So we can go ahead and write up a table to take a look at and see how we do it. So these are going to be my x's, these are going to be my y's, and after this, it's my divided difference table. Okay, so we start off by writing x1, x2, x3, x4, and maybe I'll stop at x4 here. And we write y1, y2, y3, y4. All right, now ultimately what I'm looking for is I'm looking for the term y1, y2 here. And I am looking for the term y2, y3 here. And I'm looking for the term y3, y4 here. And by the way, I should also mention that y1 in brackets is just y1. So all these guys are just level 1 brackets, but we don't really need to put those down. Okay, so good. And so now the next one I'd be looking for would go here. So it's going to be y1, y2, y3. And the next one here is going to be y2, y3, y4. And then over here is going to be y1, y2, y3, y4. Okay, so keeping this in mind, let's take a look and see what's going on here. So ultimately, if I want to figure out what y1, y2 is, well, I know that y1 minus y2, following the notation, we have y1 minus y2, sorry for small handwriting, that is going to be, why did I put a minus in there? It should not be. I just really want to put a minus for some reason. All right, so y1, y2 should be equal to just y2 minus y1 divided by x2 minus x1. Right, so that's going to give me y2 minus y1 divided by x2 minus x1. Right, so in order to write this guy, what did I need? It looks like I needed this term, subtracted this term, and I needed the difference between these two, right? Now, and so basically, now let's take a look at maybe a little bit bigger one and see what we get there. All right, so we're just trying to come up with a pattern that we can follow from this table. And so this one is going to give me y2, y3 minus y1, y2 divided by x3 minus x1. Okay, so now to compute this term, I need to go and take each of these two terms and take their difference, and then I need to take x3 and I need to take x1. So if we're using this table, then what we're going to do is we're going to take the difference between these two guys immediately to the left, and then we're going to subtract this term and the x that corresponds to the diagonal up here. So you follow up until you hit this y at the very top, and then you hit x1. And so if I was to take this difference here, I would use the difference between these two guys and then follow the diagonal until I get up to this y. Then I use this x and this x as my difference.
And if I were to use, say, this guy, I'd take a difference of these two guys, and then I'd look for the x value corresponding to this, and the x value corresponding to this, and you take their difference, right? And so that's how it goes. So you sort of build up, from the top down, just working all of these guys out in this sort of pattern, and then you'll be able to actually write everything out. Leave those guys in. So, all right, so basically, to compute an entry of this table, take the difference of the term immediately to the left with the term above the left term, right? And divide that quantity by the x value by the difference between the x value to the left and that corresponding to the y found along the diagonal. Right, it's probably the best I can explain it. So basically, you take difference of, so if I want to compute this guy, I need to take a difference of these two guys, and then I take the x value corresponding to the left, and then the x value that you get just by following the diagonal to a y value, and then that's the term you're doing here. Also, you can see, take a difference between x of 4 and x of 2, if that makes it any clearer. Okay. So why don't we go ahead and try on a specific example. All right, so let's interpolate the points. Say, you can always tell I'm just making it up. And I start with 1, I say 2, and 2, 3, and say 3, 2, and let's say 5, 20. Ha! Oh, that 520 might come back to bite me later. Okay, so let's make this table. All right, so we have our x values. That's going to be 1. It's going to be 2, 3, and 5 are my x values. All right, and my y values are 0, 3, 2, and 20. Okay. All right, so my first differences. We can do those pretty quick. We don't need one for x1. We just need to compute them. 2 for line 2, 1 for line 1, etc. And so I'm going to take so for this one, I'm going to take 3 minus 0 and divide by 2 minus 1. And so that's going to be 3, right? Let's see, for the next one, it's going to be 2 minus 3 at the top, divided by, follow a diagonal, and that y value that corresponds to it, that's going to be, so it's going to be 3 minus 2 here. that's going to be -1. And then for this one, we're going to have 20 minus 2. It's going to be 18. So 20 minus 2 divided by, let's see, 5 minus 3. Okay. That's going to give me 18 divided by 2. Okay. I should mention specifically that this is going to give us A0. This term here gives us A1. This term here gives us A2. This one gives us A3. So that's how we're getting all. That's what we're looking for. So far, what we've found is we found A1 and we found A2. Right? We're going to find A3 here. Okay, so in that brief snatch of time, my children sort of combusted and yeah, I was pulled away. Anyway, so now it's been lunch and I'm right back to this table. Okay, all right, let's see. Let's get this done. All right, so we're looking to fill in this spot here, which would end up giving us, well, let's see, this gave us A0, this gives us A1, so right now we're working on A2. And in order to get this number, we take the difference between this and this, so it's going to be -1 minus 3, and then we divide by this minus whatever it is we get when we follow this up diagonal, and so that's going to be 1, so it's going to be a 3 minus 1 on the bottom. So 3 minus 1, right? And what does that give us? That gives us -4/2, right? So minus 2. Okay, and now for the next one, we take the difference between this one and this one. These are big numbers. I mean, 18. I mean, that's almost 20. So we get the difference between 18/2 minus -1. Divide this by 5 and follow this up here. So difference between 5 and 2. So 5 minus 2. What does that give me? All right, so so it's going to be 18/2 plus 2/2 is going to give me 20/2. And this divided by 3. And so then that's going to be 20/6 altogether. And we could reduce that to be 10/3. Okay. We take a look at what we've done so far. Basically, we've computed all of the first and second differences that we need, but now we need third differences. Why is that? Well, if you take a look, here we have A0, and we just look along diagonals. This is going to give me A1. This gives me A2, but to get to A3, the last thing we need is we need to go and put something here. Okay, so let's go ahead and do that. So again, we're going to be looking at this term and taking their difference. And so that's going to be 10/3 minus -2. And we divide by this x value. And if we follow this up diagonal, we're going to have, say, this guy, and this guy. So we're going to have 5 minus 1. All right, so it's going to be 5 minus 1 here. So, putting everything together, we have 10/3 plus 2, which is also 6/3, divided by 4. And so that's going to be 16/3 or 4/3. Okay, now why don't we go ahead and actually verify that this is going to give us what we wanted. So we're looking for an interpolating polynomial that uses these, and so more or less, switch to green. We're looking for, and make it thicker. All right, let's see. So we're going to have P3 of x is equal to A0 times N0 of x plus A1 times N1 of x plus A2 times N2 of x and plus A3 times n3 of x. And here, we just found a3. That was illegible, a3. That's less illegible. Okay, so let's go ahead and do it. So a naught was 0, so 0, and n naught is the function 1. a1 is 3, and n1 is x minus x1, and x1 is just 1, plus negative 2 times n2, which is x minus 1 times x minus 2, and now we have plus a3, which is 4/3, times x minus 1, x minus 2, and x minus 3. This is x1, x2, and x3. Just happens to be 1, 2, 3. Okay, so now let's see if this actually gives us what we're looking for. You can see remnants of a mistake I made earlier, and I cut, and we'll just pretend that wasn't there. Anyway, so we're looking to check and see that we match up all of these guys. And so the first thing we do is we put in P3 of 1. What does that give me? Well, P3 of 1 should give me 0. And if I put 1 into here, 1 into here, and 1 into here, each of those little terms, each of those bases are going to be 0. So it gives me 0. All right, P3 of 2. Well, it's going to be 0 from that first term, always, plus 3 times 2 minus 1. And so that's just going to give me 3. And is that what I'm looking for? It is indeed what I'm looking for. So it's check there and check there. All right, now we have P3 of 3, and that should give me 2. And so let's see, it's going to be 0 plus 3 times 2 plus negative 2 times 2 minus 1 times 3 minus 2. And so what does that give me? It gives me 6 minus 2 times did I make a mistake? Let me go back and check that. All right. Stay focused. All right, don't panic. Everything's okay. So we have P3 of 3 should be giving me what? So if I out of this term, it's just going to give me 0, plus out of this term, that's going to give me 3 times 2, right? Now the next term is going to give me minus 2 times 3 minus 1, so it gives me 2, and 3 times 3 minus 2, that gives you 1, and then the next term is just going to give me 0. And so that's going to give me 6 minus 4. There we go. All right, so that worked. It's 2. And now we get the P3 and just check 5 because we've confirmed that this works. All right, so we put 5 in, we get 0 plus 3 times 4, that's 12. Minus 2 times 5 minus 1, that's 4. 5 minus 2, that's 3, so that's minus 2 times 12. And then plus 4/3 of 5 minus 1 is 4, 5 minus 2 is 3, 5 minus 3 is 2, so that ends up being 24. Yep, cool. All right, so let's keep moving. So that is 12 minus 2 times 12 gives me minus 12, plus, let's see, 3 goes in 24 8 times 4, so that's 4 times 8, that is 32, so that is minus 12 plus 32, and indeed that is 20. Check. Okay, good. So we made an interpolating polynomial. Okay, cool. So that was using Newton's method. It was relatively pain-free, except for me having to go put out a fire with my children. And yeah, cool. So I guess we'll leave it there and head back to the office.
Okay, so am I recording? It's hard to tell on this thing. Yep, recording. Okay, so we're back, and yeah, and thanks for listening to the lecture. So yeah, Newton's divided differences. There's a nice little table that we can put together to help work out exactly what those are. It's a recursive algorithm, and so tables actually help out a good deal. And so so when you need to work it out, say for the exam or anything else, there's a nice little algorithm that you can use in tandem with the table. But yeah, so we're going to see these things rear their head again when we talk about numerical differentiation and integration. And yeah, so it's really important to make sure we really get down what we mean by all this. In any case, I need to go figure out why my camera's not working. It's not cheap, and that's rather disconcerting, especially since it's become my job to record. So yeah, I need to figure that out. Got a new ring light though. My wife got it for us for our anniversary. So yeah, that's fun. It checks out. It does different colors. So boop, boop. Yeah, I don't know where I started. There we go. That looks white enough. Anyway, yeah, cool. So thanks for listening, and I hope this video is actually somewhat legible, coherent. I hope you can hear me. Maybe get that camera fixed. All right, thanks for watching.